So in this section, we're talking about chords and secants in a circle and how they, what happens when they intersect with each other. So we've already studied this once, even though we didn't talk about it as an intersection of two chords or two secants. First, let me define secant for you. So a chord was a line, a segment that has endpoints on the circle. If you remember, a tangent line is a line that intersects a circle once. A secant is a line, so it goes on forever, not a segment, a line that intersects a circle twice. We call that a secant. Okay, and so one of the things we learned about is that when you have a line like that, if it intersects on the circle, then this angle here is the same as that angle. And this angle is exactly half, this is our arc AB, the measure of AB, right? That is the inscribed angle theorem, right? Central angle, the arc is the same as the angle. Inscribed angle, the arc is twice the angle. Well, the two secants don't have to intersect on the circle or at the center. They can also intersect in other places. For example, you could have two secants like this that intersect like that. This point right here is not on the circle, so it's not inscribed. It's not at the center, so it's not a central angle. So the question is, how do we find out the measure of that angle? Well, it turns out there's a nice theorem associated with that. And so that theorem, and it has what we'll see actual 3 parts, and it's theorem 11.11. And the 3 parts are the measure of an angle formed by the intersection of two secants that, and then there's 2 possibilities. One, intersect inside the circle. That's this case right here. Well, that angle, so this angle right here, or possibly this angle, we can do both of those. It turns out that it is equivalent, intersects inside the circle, is 1/2 the sum of the 2 intercepted arcs. And so we have a circle that looks like this. We've got 2 secants. We call this point A, B, C, and D. We'll call this point E. Well, the measure of angle AEB, so this angle right here, is going to equal 1/2 the measure, well, the intercepted arcs for that angle is this one and this one. Because remember, this angle, these 2 angles, AEB and CED, are the same, so we're considering both of those. So the 2 arcs that it intercepts are those AB and CD. So it's going to be the measure of arc AB plus the measure of arc CD. In the same way, we could say the measure of AEC, that's this angle right here, is just 1/2 the sum of the measure of arc AC plus the measure of arc CD. Not CD, BD. So it's very simple. All you do is you find those 2 arcs, you take the average of them, right? Add them together, divide by 2, that's the average of the 2 arcs, and that is the angle that is between those. And then the other case, if you have 2 secants that intersect outside the circle. right? So the measure of the angle formed by two secants that intersect outside the circle is 1/2 the difference. Inside the circle is sum, outside the circle is difference. The two intercepted arcs. Remember, intercepted means the arcs in between the angle. So the difference here is our two lines that we draw, they don't intersect on the circle, they don't intersect inside the circle, they intersect outside the circle. And so if we call these, again, A, B, C, D, and this E, then what we're talking about is the measure of angle AEB. This is the measure of the angle created by these two secants, right, if they go on like this. Well, they are going to equal 1/2, and instead of adding A, B, and CD like we did in the part 1, we're going to subtract them. The measure of CD minus the measure of AB. And you just subtract those two measures. Note that AB, there's one of these is clearly smaller. AB is clearly smaller than CD. That will always be the case. That's the one that's subtracted. You should always end up with a positive answer. So it shouldn't really become an issue or a thing, but that's what your answer is going to be. And so those are your two theorems about secants that intersect inside the circle and outside the circle. Now, there are a couple special cases to this one. If one of them is a secant and one is a tangent line like this, then again, the only difference is, right, when you look at your arcs, this one is just going to be, so the measure of AEB, you're just going to do measure of arc BC minus measure of arc AB, right? You see how that one works? And then the last special case is when you've got two tangents. And so there's only 2 points that actually matter here. And so for that one, this is a definite special case. And so because if we add a third point here, it's going to be the measure of arc ACB minus measure of arc AB. But don't forget that those two arcs, ACB, this arc, all the way from A to B going that long way, and A to B the short way, those actually add up to 360. So that kind of becomes some special things happening because you have this additional information that you know the sum of those two arcs is 360. And so that helps you solve problems involving them. All right, let's do some examples about this. And so the measure of arc CD is going to be 38. The measure of arc BE is going to be 164. And so you're asked to find the measure of angle DFB. So this angle right here is the one that you're asked to find. Well, when you look at this, based on our theorem, we know that you got two chords that intersect inside the circle. So the angle is going to be the average of those two arcs. However, I don't want to go find this one first. Instead, let's find that one and then use the fact that those are a linear pair of angles. So y is just going to be 1/2 times the sum. Intersect inside the circle, it's going to be the sum of the two arcs. And so 164 plus 38 divided by, we've already divided by 2 by multiplying by 1/2. So 164 plus 38, that equals 202. 202 times 1/2 equals 101. So y is 101, and so the measure of angle, if this turns out to be 101, then the answer to my problem, DFB, is 79 degrees. And so it's 79 degrees. You don't know exactly what BD and EC are. We don't know those exact values. And so we use the other two first, and then we go from there. All right, for number 2, you got the measure of DB is 74. The measure of DFB, this one right here, is 83. Oh, my bad. Measure of angle DFB. And so this angle right here is 83. And you want to find out what the measure of arc CE is. Well, this is one where you're going to have to do some algebra. This angle is an angle at the intersection of two chords inside a circle. So that value, that angle, 83, is equal to the average, or 1/2, times the sum of the two arcs it intercepts. So you can just write an algebraic equation, 83 equals 1/2 times 74 plus x. Now we just go through and solve this equation, multiply through the whole thing through by 2. We get 166 equals 74 plus x. So x turns out to equal 92. When you subtract 166 minus 74, you get 92 as your answer. And so you can just apply your equation, your formulas to that. All right, for number 3 here, if you take a look at it, this one is different because we have a tangent line. And so it says you need to find out what x is. Now, what's hard about this one is it appears we don't have a ton of information. And so we have to write this one because we know that 38 is going to equal 1/2. The intersection point is outside the circle, so we're going to need to subtract our arc measures. But the problem is we don't have a value for that one, but we can find it in terms of x, because this is going to equal 360 degrees minus 140 minus this length, which is x. And so that turns out to just be 220 minus x. So now we know this length is 220 minus x, and we know this length is x, and so we can do it as 220 minus x, and we're ready to go. So that's going to give me 38 equals 110 minus x when you multiply through this by 1/2. And so x turns out that it will equal 110 minus 38, which gives you 72. And so that means that x is 72. All right, this problem is a circle that's inscribed in a triangle. It seems like it maybe is a little bit complicated, but it actually doesn't turn out to be too bad. But let's just look at it from the perspective of just one of the values. So we'll do x here. And so it looks like this, where we're trying to find out what x is. We know that this equals 117 up to this point over here, right? That's this length, this arc right here. And this one turns out to be 121. And so we can actually find out what this arc is by doing 360 minus 117 minus 121. And when you do that math, it turns out to be 122. And so there are actually 2 ways to solve this. The first way to solve it is just to do, well, it's an intersection of 2 tangents outside the circle, and so it's going to be 1/2 times the difference between the 2 arcs. The first arc is the one that goes all the way around, which is 121 plus 117, and so that turns out to be 238 minus 122. That is 116. 1/2 times 116 turns out to be 58. Now, if you are good with some quick calculations and you are curious about some numbers, you might notice that 58 and 122 are supplementary with each other. Well, it turns out that that's always going to be the case in this example, and that is because the other way we could have done this is instead to think about a central angle, which would have been to draw this in like this. Since these are tangent lines, these are both 90 degrees. And so this would be a kite. Remember, we learned that if you got a point outside the circle, the lines are equidistant. And so that means that this angle and this angle have to add up to 180 because these are both 90 degrees. And so that means this angle and this central angle are supplementary, but this arc is just equal to the central angle. So if this is 122, because that was the arc, and that means that x has to be 180 minus 122. So that means x is 58, z is going to be 63, and y is going to be 59, because we can just do 180 minus 117 and 180 minus 121 to find out those other two angles. All right, last one here. This one looks like we don't have a lot of information about it. You have to notice that this is a right angle because it's inscribed in a semicircle. This is the diameter of the circle. And so this has to be 90 degrees. It's an inscribed angle, and it's half of 180, right? This is a 180 degree arc right there. And this is exactly half this length. And so this turns out to be a 30, 60, 90 triangle. That's a hard part on this problem, is recognizing, okay, that's 30, this is 60. Well, if that's the case, that means that this arc right here is 120. And so this arc right here is 240. So intersect outside the circle, you get 1/2 times 240 minus 120, and that equals 60. And so the correct answer on that one is 60 degrees.